We are watching AI outgrow the planet, not metaphorically, physically. Gigawatt-scale data centers are rising everywhere. Some already consume as much power as entire countries. And the roadmap says we need 100 times more compute. But a small team of engineers is claiming something uncomfortable, that the direction where we are going may be wrong. So they went back to the first principles and built a new kind of optical chip, based on a different class of transistors, so-called Metasurfaces. And this new chip delivers the compute of 100 GPUs in the footprint of one, while using roughly 1% of power. If that holds up, it breaks the core belief the entire AI industry runs on, that intelligence scales with energy. I'm a chip design engineer, and I know exactly what you're thinking. These numbers sound too good to be true. Subscribe to the channel and let me show you why they might be actually right. For decades, computing followed one simple rule: make transistors smaller, put more of them on a chip, get faster. That rule gave us everything: smartphones, the cloud, modern AI. And then, over time, transistor scaling slowed. Power stopped scaling down. AI didn't wait. So the industry adapted. We stopped making computer chips smaller and started making them bigger. We began connecting more chips, stacking them together, both horizontally and vertically, squeezing performance out of scale instead of physics. Without saying it out loud, we all accepted that intelligence has a fixed energy cost, and the only way forward is to pay it. So when AI models exploded in size, the logic felt obvious. Build more compute, build larger data centers, build the power plants to feed them. But when I look at this 5 gigawatt data center being built in northern Louisiana, something doesn't sit right. Because the real bottleneck isn't compute, it's energy per operation.
The amount of computation we need at this point, as a result of agentic AI, as a result of reasoning, is easily 100 times more than we thought we needed this time last year.
If you take a 700-watt NVIDIA GPU and try to make it 100 times faster without changing how computation itself is done, you don't get the progress. You get a chip that burns 70 kilowatts and melts the moment you turn it on. This is where the current roadmap stops making sense. So if we want AI chips to be 100 times faster, we need different physics. So where do you even look for an answer like that? Well, you actually start with the workload itself. Modern AI is dominated by one operation: matrix multiplication. And we actually solved this one before, with systolic arrays. Instead of shuttling data back and forth between compute and memory, you load it once and then reuse it many times. That's the trick. And that saves us a lot of energy, because this memory access is exactly where the most energy goes. This idea dates back to the 1970s, and for a while it was forgotten. Until 2017, when Google brought it back with its custom AI chip, so-called TPU, Tensor Processing Unit. This is Google's custom AI chip built around exactly this concept, and it worked extremely well. And this gave them one of the most efficient AI silicon in the world to date, competing with NVIDIA GPUs, powering models like Gemini and attracting customers like Anthropic. And in the digital world, this approach is brilliant, up to some point, while arrays stay small. Because as we push to larger and larger matrices, these arrays have to grow. And as they grow larger, power starts to scale with area. At that point, most of the energy is no longer spent moving data. It's burnt inside the compute units. Every multiply, every accumulate, every clock tick. Heat builds up faster than you can remove it. Performance stalls. This is where digital arrays stop scaling. So researchers took the next logical step. Not better architectures. A fundamentally different approach to computing: analog. Analog systems are linear physical systems, and matrix multiplication are linear operations. So you see, these sort of were meant for each other. In analog computing, most of the energy is burned at the perimeter. That's where you inject inputs and read out results. Inside the array, nothing is switching on or off. And this is beautiful because the computation is happening passively as signals propagate through the physical system. As you scale the array larger and larger, the interior doesn't become more expensive, only the edges do. So the total energy stays roughly the same. And that efficiency is exactly what AI needs. So everyone rushed in. A wave of analog chips followed. And for a very brief moment, this looked like an answer. But most of the analog chips failed or walking dead. And there were many reasons, but one problem showed up again and again. They were still built with electronics, resistors and capacitors, and those don't move signals instantly. They have to charge and discharge, and this introduces delays and dissipates energy. As arrays grow larger, those delays pile up, noise increases, control becomes harder. So while the math was right, the medium wasn't. So the industry abandoned analog. But what if analog was actually right, but electronics wasn't? This is the moment engineers get uncomfortable, because it's one thing to optimize architectures and another to question the medium itself. What if instead of pushing electrons through wires, we used light? Signals that propagate instantly without resistance. Now, if we imagine building these systolic arrays with optical components, something strange happens. Every time you double the size, you don't just get double compute, you turn energy efficiency into speed. Because when we make this chip bigger, we get way more compute than extra power cost. That shouldn't be possible, yet it is. And you may say, well, people already tried to build it, optical computing chips. And you're right, optical computing has been a dream for decades. But it remained a dream for one simple reason. Traditional optical transistors are enormously large. Look at this one, it's 5 millimeters. Now compare that to silicon transistors. Today we are talking about transistors with features just a few nanometers wide. You see, it's not even the same universe. And this size kills scaling even before you get started. And that's why optical computing never stood a chance. Not against GPUs. These scaled too well. But then something changed. This is Metasurface, a Texas-based startup backed by funds of Bill Gates, Jeff Bezos, and Michael Bloomberg. And that matters because they backed the Metasurface at this specific moment of time when AI data centers started turning into energy problem. What's so interesting, their goal is not to replace the GPU ecosystem, it's to plug into it. Look at this one. Right next to the chip there is a red glowing block. It almost looks out of place. It made me very curious. That's actually the optical compute module. This is where the math happens using light interacting with metasurfaces. In a moment, I will show you how this exactly works and why this matters. But before that, look at this. AI models are getting scary good at image and video generation. The problem is, to get good results, you usually need multiple subscriptions and to be really good at prompting. Until now. Last week, I've been testing the new Clink 3.0 model on Higgsfield. And this is the first model where I moved from trial and error to actually directing the output. What makes it different? It's been trained as a unified multimodal model. Everything trained together natively. Text to video, image to video, reference to video. Look what it can do. I upload a character reference, write a scene description, and the model generates a multi-shot sequence with different angles and camera movements in one generation. The character stays the same character. And here is a wild part. You can add dialogue directly in the model, in multiple languages, and it syncs naturally with character expressions and emotion.
These data centers consume far too much power.
Physics works. Impressive cinematic shots, controlled motion. If you are creating content with AI, this is honestly a game changer. And Higgsfield has unlimited access to Kling 3.0. And right now they are offering 70% off premium plans. If you want to try it, use my link below to get the best deal. And thanks to Higgsfield AI for sponsoring this episode. Now let's get back to the light, because what Metasurface built follows a very particular philosophy. Their chip is built the same way GPUs are built today. Same foundries, same supply chain, same packaging logic. So from the outside, this still looks familiar, but inside everything flips. In a normal GPU, compute cores constantly pull data from memory. That back and forth is where the most of the energy goes. Metasurface flips this idea. Here, the memory is the computation. This chip still uses familiar packaging. High bandwidth memory sits beside the optical chip, and the small electronic controller drives everything. But the key difference where the weights of neural network live. So instead of storing them as digital bits, they are stored physically in the metasurface, written in how it reflects and shapes light. Light hits the surface, and the math happens instantly at the point of the contact. So how does this suddenly become possible? Their breakthrough is actually in the metasurface. And this didn't come out of nowhere. Patrick Bowen spent years working on metasurfaces long before AI pushed data centers to the edge. Originally, metasurfaces are about controlling light, making optics smaller, more precise. But then, in this process, a different idea emerged. If we can control light that precisely, maybe we can also use it for computing. So, what is a metasurface? Imagine an ultra-thin glass. Flatter than a mirror, but instead of being smooth, it's covered with millions of tiny patterns. This is a physical instruction set. When light hits this surface, these instructions decide what happens. They bend it, shift phase, redirect, all at once without any moving parts. Before, they were never used for computing, because traditional metasurfaces are static. Once etched, they're fixed. Forever. Imagine it like burning in the numbers right into the hardware. This is great for lenses, but not so useful for computing. Metasurface changed that. They've built an active metasurface device where that function can be written and then rewritten electronically. And now finally it starts to look less like a lens and more like a photonic memory. Now imagine each pixel contains millions of tiny cells, and each of the cells can be programmed, its reflection and the phase shift, by applying the voltage to the cell. And now it looks more like an optical DRAM, which is done using the standard foundry process. Now imagine a beam of light coming in. The brightness of that light encodes input data. Brighter means larger value. Dimmer means smaller value, and that light hits a pixel with a certain reflectivity. If the pixel reflects half the light, the output becomes half as strong. So here, input light times reflectivity equals output light. That is multiplication, done directly in physics. And these optical cells are extremely small, up to 10,000 times smaller than traditional optical devices. This means we can pack millions of them in a chip. And when the upcoming light hits the surface, every pixel multiplies once, but all of them are doing it at the same time. The reflection itself performs the math. And the result is a dense optical matrix multiplier working at the speed of light. And when you cross that threshold, something strange happens. Throughput starts scaling with area. So when you make the chip bigger, it actually gets better. According to Metasurface, a single unit can reach 1.2 million tera operations per second. And when you place 8 of these units in a tray, they project performance that can exceed the entire GPU rack using a fraction of the energy. If this holds at the system scale, the implications are beyond more efficient chips. It will change the entire AI data center economics. This means power stops being the primary constraint for scaling. And that matters because this changes where AI can run, who can afford it, and how fast it can grow. Which raises the obvious question. Do we actually want that? Because half of the internet is really scared of AI. And now we are talking about removing one of the last things that slows it down. So what they have actually shown? They have already a working test chip, a prototype in silicon, and basically they've already de-risked all the fundamental physics. The computing cores run at 56 GHz. That sounds absurdly fast, and it is, but there is a reason for that. As we just discussed, there are very little things inside that slows the signal down. There are no electrons pushing through resistance. There are no capacitance that have to be charged and discharged. No long metal wires heating up. That's the reason why traditional silicon chips hit a wall at a few gigahertz. But this chip doesn't play by those rules. Because the physics itself underneath is different, and this shows up in efficiency. These are the measurements from their paper. For reference, NVIDIA Blackwell GPU delivers about 9 peta operations of compute at roughly 1000 watts. That lands around 9 TOPS per watt efficiency. While this new chip, at peak, targets about 235 peta operations per second at 675 watts of power. So they report roughly 30 times better efficiency than today's state-of-the-art NVIDIA GPU. And that's why they are targeting hyperscalers first, inference applications, where efficiency matters more than raw peak performance. You can think of workloads like search and ranking and real-time inference behind ChatGPT and image generation. These systems run all the time, and they dominate data center energy use. And if you can cut power there, the impact compounds quickly. Their roadmap points to data center-ready systems around 2028. I personally think it's a little bit optimistic, but it's close enough so that the industry can't ignore it. And this matters for one more reason. It is designed to be manufactured at factories like TSMC, on standard silicon photonic process. And this means it fits into existing semiconductor supply chain. And that makes a huge difference between an idea, a lab experiment, and something that can be actually scaled. Here is a problem. Every few years, someone claims that optical computing will replace GPUs. And almost every time it fails when scaling starts. Startups don't win on physics alone. Because physics alone doesn't decide winners. Ecosystems do. Manufacturing metasurfaces at scale is hard. What works on test silicon does not automatically survive real production. Those large arrays introduce defects. Thermal stability becomes a problem. So far, the results are at prototype scale, and the next step is proving that they can scale reliably. And then there is software, because hardware doesn't win without the ecosystem. GPUs have decades of momentum. Compilers, frameworks, entire teams have been built around them. And in general, competing with NVIDIA Blackwell GPU, which is already shipping at massive scale, or upcoming Rubin GPU, sets an extremely high bar. For Norifos, proving that physics work is just the first step. They also have to prove software compatibility and cost parity. And they have to do it fast, because by the time their early data center prototypes arrive, NVIDIA will not be standing still. This is definitely one of the most exciting bets in modern computing, but history isn't kind here. Optical computing startups have hit this wall before. Many of them never made it past the lab, because hyperscalers didn't want to take this risk. The physics is compelling, the prototypes are real, but scale is the test. Still, the future of computing looks Right. It definitely won't be purely electronic anymore, but it won't be photonic either. It will be heterogeneous. And for the first time, power may be not the limit. If, and it's a very big if, the ecosystem can move fast enough to catch up with the physics. Now, if you want to go deeper, watch this episode where I break down the insane story of the world's largest AI data center. You will love it. Or this one, where I explain what it takes to invent the smallest microchip technology to date. And remember to subscribe to the channel. I will see you there. Ciao.